Hey folks, today's lesson is all about Newton's first law. We will study each law individually. There'll be a short gap between the first law and the second law, and a longer gap between the second law and the third law, and we'll cover them kind of over the span of the unit. Newton's first law is the most straightforward and requires the least amount of prior knowledge, so that's why we start with it. It's also the one that's the most wordy, and so it has two parts. First one is an object in motion will stay in motion with a constant velocity unless acted on by a net external force. And so we're going to just like unpack that phrase or that sentence right now. An object in motion will stay in motion with a constant velocity. So um, constant velocity means the acceleration is zero. That'll be important later. Um, and if it's already in motion, its velocity will stay the same. Okay, that's great. Unless acted on by a net external force. So we know a force is a push or pull. To say something is external is to say it comes from outside. So it has to be a force that comes from outside the object. I guess an example would be if you are sitting in a car and you like push on the steering wheel, you can't move the car just by pushing on the steering wheel. So that would be an internal force as opposed to an external force. And then to say a net external force, we haven't defined that yet, but a net force is the overall force. So if you and a friend are both pushing against one another, um, we'll talk about this more later, but if you're pushing against one another and you're not moving, or let's say you're engaged in a tug of war and you're both pulling but you're not moving, we would say that the net force on everything is zero, that it's all balanced. So a net external force is a situation where the forces don't balance, and that leads to a change in motion. So if there is a net external force, then the object will change its motion. But if there is a net external force of zero, or in other words, if all the forces are balanced, then the object will remain at constant velocity. I have the word, these are my class notes, so I have the word pucks over here, and I would just think about like a hockey puck. You can like stand at one end of an ice rink, and especially if the Zamboni has come through recently, you can shoot the puck across the rink, and it will glide with very close to constant velocity until it hits something. And so that's Newton's first law in action, is that if you set a hockey puck in motion, it will slide very easily across the ice um, until it hits something. And the hitting something is the net external force. So that's going to change the motion. So really, like we're seeing that Newton's first law is just conceptualizing the idea of a net external force. The second half is an object at rest will stay at rest unless acted upon by a net external force. So that one's actually a little easier. And my demonstration in class would have been to put my water bottle on the desk and then tell you that I was now demonstrating this part of Newton's second law because the water bottle's at rest. And as long as nothing is causing the net force to be unbalanced, then it will just sit there. I can unbalance that force by like moving it along or picking it up and putting it down. But if I just let it sit there, it will stay there. And so, the like one-liner of Newton's first law would be objects will just keep doing what they're already doing unless you apply a net force to them. So that's the like text of Newton's first law. And to say a little bit more about that, if we consider like different perspectives, oh, actually, sorry. So we start with inertia. Um, Newton's first law is based off of Galileo's law of inertia or understanding of inertia. And so we define inertia as an object's tendency to follow Newton's first law. So kind of think of that as how effectively will it continue in constant velocity motion or continue to be at rest when it is subjected to a net external force? So the more inertia something has, the more it will retain its motion, or the more effectively it will retain its motion when subjected to a force. It's proportional to mass, so it kind of makes sense. If you're trying to move a chair, you can just kind of like pick it up and move it around. If you're trying to move a refrigerator, you need a lot more force to get that refrigerator like slide around your kitchen. And so inertia is something that all objects have as long as they have mass. The more mass they have, the more inertia they have, and the more difficult it is to make a big change in the velocity of an object. To kind of go back to the fact that there's two statements here, one kind of thought consequence of Newton's first law is to say that being at rest and moving with constant velocity are pretty much equivalent according to Newton's first law. And I say here passenger on the train. And so I would say, like, let's say you're taking a train into Boston with your friend and you're sitting next to your friend. Um, you also see a friend like standing at the train station that you're like driving by, that you're on the train traveling by. Um, or maybe they're just like randomly stuck at the train crossing as the train goes by. We imagine the train is moving with constant velocity. And both of the people in your life can see you from where they sit or stand. Your friend is sitting right next to you. And so even though the train is moving, um, just from your friend's perspective, your location relative to your friend is not changing. And so you are essentially at rest relative to your friend. Um, on the other hand, your friend who's like outside the train, sitting at the crossing um, sign, waiting for the train to go by, they're at rest and they're seeing you travel by at some constant velocity. So, from your friend's perspective inside the train, you're at rest. From your friend's perspective outside the train, you're moving with constant velocity, but you are obeying Newton's first law in both situations because you are maintaining that constant velocity because all of the forces on you are balanced. So, even if you change your perspective, Newton's first law should hold true, and there's some equivalence between being at rest and moving with constant velocity. The last thing to kind of add to this before we get to some examples is this idea of an inertial reference frame. In AP Physics 1, we make the assumption that all frames of reference are inertial, and that basically means that we get to use all the physics equations that we know and all the physics understanding that we've learned. So to say a frame of reference is inertial is to say it's one in which the first law, or Newton's first law, holds true. To be very specific, it is a frame of reference that is not accelerating. And so I'm going to give you an example. Let's say I was driving to school one day and I was in a rush. I had my like coffee mug ready to go. And when I got into my car, I put my coffee cup on the top of like the roof of my car. And then I got in and I started driving, but I forgot that the coffee mug was on the roof of my car. So I like accelerate very gently, and for whatever reason, the coffee mug stays on my car as I'm driving. And I get onto like the main road and I'm going at like 40 miles an hour, and I see like a squirrel start to cross the road and I slam on the brakes. And so I slam on the brakes, and what happens to my coffee mug is it flies forward. Now, Newton's first law would say about the coffee cup that it continued to move straight ahead because there was no net force acting on it. So it obeyed Newton's first law by just continuing at approximately the velocity of the car as soon as I stopped the car. Um, After that, if I want to give another example, Newton's first law was also being obeyed because as soon as the coffee cup was no longer above my car, it starts to fall. And that's a change in velocity that we've talked about with projectiles. And so it's changing its velocity because the forces on it were not balanced any longer. So there's kind of two stages. While the coffee cup is like flying off my car, it's still moving at constant velocity and obeying Newton's first law. As soon as it's off the roof of my car, it starts to fall. That also obeys Newton's first law because there is a net external force that's bringing my coffee mug down. So let's talk about different perspectives. From my perspective, I slammed on the brakes and my speed is going from 40 miles an hour down to zero very rapidly. I am in what is called a non-inertial reference frame, meaning I'm accelerating. And if I didn't know better, I would say that something threw the coffee mug off of my roof. If I had even let's say I had a sunroof in my car and I like looked up and I was like, oh crap, there's a coffee mug in my car. I'm going 40 miles an hour. And then I slammed on the brakes. It would look like the coffee cup just started to fly off the car. And so in a non-inertial reference frame, it appears that things are disobeying Newton's first law. I would have to make up a force in this situation to explain what was happening, to say that something must have pushed the mug off of my car. From the perspective of the squirrel, everything's fine. They're standing in the middle of the road. They are in an inertial reference frame. They see me and the coffee mug in my car coming toward them, and then they see my car stop, but the mug keeps going. And so the mug obeyed Newton's first law by continuing at constant velocity and then falling to the ground. So this doesn't come up a lot, but it's important to understand that depending on what your body is doing, you might not be able to see things obey Newton's first law. Okay, so there's a couple examples that I wanted to go through, and I'm just going to cover that up and go back to this thing here. And so my questions are as follows. There are things I want you to notice. When you're in a car the next time and you take a turn, you've probably noticed that if, the driver takes the wheel and turns the car to the left, your body like gets thrown to the right a little bit and vice versa. And the more severely they turn, the more severely your body gets thrown. But what you want to understand is when you start to turn the car, when you turn the wheel, the force that causes the car to turn comes from the road, and the road is causing your car to turn, but the road doesn't touch your body. And so your body doesn't actually get thrown to the side. Your body continues moving straight ahead while the car moves to the side. So the reason you get like slammed into the window or the side of the car is because your body's inertia carries it forward while the car changes direction. So that's one example. Next example is a rattle. I would like make rattles for my son by just taking like an empty plastic bottle or jar and putting like something plastic and loud inside, and he would just like shake it, and that was entertaining. So how a rattle works. So let's imagine that there's something at the bottom of the rattle, and he starts to shake it. Well, he makes like this motion. He just like pulls it up, and what that does is he exerts a force on the rattle, and the rattle exerts a force on all the little beads on the inside. And so he's pushing the rattle and all the beads upwards. Well, to make the sound, a baby will do this with the rattle. So they'll move their hand up, everything will get pushed up, and then they'll move their hand down. But because the beads on the inside aren't connected to the rattle itself, the rattle changes direction, but the beads keep going and they hit the top of the rattle and they make a noise. And so anything that has like loose stuff on the inside that you shake demonstrates Newton's first law, that the change in motion of the stuff on the inside is delayed because you exert a force on the thing you're holding, but there's nothing right there to change the direction of the little pieces. Things I want you to think about would be when like a dog gets out of the water, it shakes its body to get the water out. And so I would ask you to think about like how a dog does that in a way that propels the water away from its body. And I think that might be it. So we will discuss more first law examples in class, but that is a hopefully thorough intro to the topic itself.